Okay, now let's study the vector valued functions. Vector valued functions and parametric curve. What is the vector valued function? Suppose there is a particle move along the space like a plane over some time interval. Then its coordinate are functions of time t. T belongs to some interval. Then when t move along the interval, the coordinate, its coordinate draws a graph like this, and its coordinate actually is, and for this curve actually has the equation, the parametric equation, that is x equals xt, y equals yt, and z equals zt. This is t belongs to I, t in I. This is a parametric equation of the curve C. If we write all the coordinates, if we regard the coordinates as coordinates of a vector, we write this vector as RT because the coordinates is depend on the time t. Then we call the RT as a vector valued function because its value, its range, this range are vectors. We call the RT is a vector valued function. And the tip of this vector valued functions, this vector valued function is actually a curve in the space. So vector valued function of one variable is actually a curve, is a parametric curve. Vector valued function, and any vector valued function of one parameter t corresponds to a curve. Any vector valued function corresponds to a curve. Just like the any vector corresponds to a point. That's similar with this result, because the vector function, the tip of the vector function is actually a space curve, and this curve is a parametric curve. Parametric curve with parameter t. So this is vector valued function, and for vector valued function there are also concepts of limit, continuity, and derivative and integration. First, let's define the limit of a vector valued function. The limit t tends to t naught rt actually is defined as limit t tends to t naught xt, limit t tends to t naught yt, and limit t tends to t naught ct. That's the definition or the computation for limit. But if we use the formal definition for limit, the definition is limit t tends to t naught rt equals maybe some vector. We write this vector as L. That means for any epsilon greater than 0, there exists delta greater than 0 such that when t minus t naught, the absolute value less than delta greater than 0, the inequality rt minus the vector L, the length of rt minus the L is less than epsilon holds. Then we say that the limit of rt is the vector L. That's the formal definition for limit, and the computation is the above equality. So there's nothing new for the limit of vector valued function. Just the three scalar function, the limit of the three scalar function. If all three limits exist, then we say that the vector function has limit. And the continuity. We say that R when t tends to t naught, rt equals rt naught. We say that rt is continuous at t equals t naught. Okay, that's the definition for limit and continuity. Let's take our example. Find limit t tends to 0, rt, where rt equals 1 plus t cube I plus t e negative t j plus sin t over t k. The solution is we take the three limit for the component of RT, because limit t tends to 0, 1 plus t cube equals 1, and limit t tends to 0, t e of negative t, that is 0, and t tends to 0, sin t over t, that is 1. So limit t tends to 0, RT, that is I plus k, or just write as 1, 0, 1. Okay, that's the limit and continuity. The fourth as derivative. We write r, the derivative of RT at t naught, that is limit delta t tends to 0, RT minus RT naught plus delta t minus RT naught over delta t, or write as limit t tends to t naught, RT minus RT naught over t minus t naught. The computation actually is equal to x, the derivative of x, the derivative of y, and the derivative of z. Actually is here. And for any t, the derivative of any t, that is limit delta t tends to 0, RT plus delta t minus RT over delta t. And what's the meaning of derivative? We know that for scalar function, the derivative at that point is the slope of tangent line. But for the vector valued function, the derivative we just write the result. RT, the derivative of RT is our tangent vector. Of RT at t. This is curve, and each point is a vector. That's RT, and this is the RT plus delta t. Then the RT plus delta t is this vector. So this vector is RT plus delta t minus RT. when t tends to 0, when t tends to 0, that is that when t tends to 0, then RT plus delta t minus RT is this one. So this is RT prime. So it's a tangent vector of RT at t at this point. And there's some other definitions. Some definition, that is motion, velocity, and speed, acceleration. That's the physical concept for the derivative of RT. What is motion of a particle? Motion of a particle, that is just RT itself, and its velocity of a particle is sometimes we write as Vt. We write as V, the vector. Vt is the derivative of RT. And speed is the length of Vt. We just write as the scalar is the length of velocity. And acceleration is it we write as A, the vector A, vector At. That is the second derivative of RT. That's the those are concepts from physics. The second example, if RT equals the same thing, 1 plus t cube, we write as coordinates t e negative t and sine t, maybe a different one, sine 2t. Find the velocity, speed, and acceleration of RT at t equals 0. So the velocity is the derivative of RT, that is 3t squared as e negative t minus t e negative t and 2 cosine 2t, and acceleration t, that is double the second derivative of RT, that is 6t negative e negative negative 2 e negative t and plus t e of negative t, that is 4 sine 2t, negative 4 sine 2t. So v at 0, that is 0, 1, that's 2. So the speed is square root 1 plus 4, that is square root 5. And acceleration at t, that is 0, negative 2, and 0. Some physical concept. And the derivative rules for rules of derivative. Because for vector, there's there's inner product and cross product and multiplication by a scalar function. The first one is addition and subtraction, ut plus vt, and the derivative for addition and subtraction, that is, take the derivative first and add or subtract or add or subtract second this and the next. And for some constant multiplication, c times ut, we can take the constant outside. This is similar to the scalar function. But if there's scalar function times a vector valued function, actually that's the same as product rule, df dt times ut plus ft times du dt. The fourth one is the product rule for dot product. Product rule for dot product. If ut dot product vt, then take the derivative. That is the derivative of u dot v plus u dot dv dt. That's to say, the form is similar to scalar function, but for cross product ut cross vt, that is du dt cross vt plus ut cross dv dt. And there's chain rule. If d dt, if u is a function of ft, then it's du, we can write as u, we'd better use another symbol, that is u prime as for ft. We view ft as a whole, then times f, the derivative of f. Actually, these rules can be proved directly. So we don't want to prove it. Prove the and integrals. From a to b rt dt is actually the integral from a to b x 关于 x t, the xt dt, and a to b yt dt, and from a to b zt dt, and together, or write as a to b xt dt I plus a to b yt dt j plus from a to b zt dt times k. And there's a fundamental theorem. If from a to b r prime t dt, that is r b minus r a. That's the fundamental theorem for the vector valued functions. So there's nothing special here. There's nothing special here. Just take the derivative, integration, limit for each component. Okay, that's the vector valued function and parametric equation, parametric curve. Actually, our vector function corresponds to our parametric curve.